Okay, we will go ahead and get started. So thank you everyone for joining us for this month's CTSC Distinguished Speaker Series. So this is a monthly seminar series that highlights nationally recognized researchers in clinical and translational science. So those of you who are not familiar with our CTSC, the goal is to improve the health of people who live in Northern Ohio by providing resources and services to our hospital and university partners, clinical and translational researchers and scientists, as well as community members. The CTSC is currently doing this by focusing on these 5 key areas and initiatives. So these are resources and services, workforce development, community engagement, health informatics, and clinical and translational funding opportunities. And I just wanted to take a minute to introduce our speaker for today. So Dr. Payne is joining us. He serves as the Chief Health AI Officer for the BJC Health System and Washington University School of Medicine. And he's also the founding director of their Joint Center for Health AI. He also holds the Janet and Bernard Becker Professorship and is the founding director of the Institute for Informatics, Data Science, and Biostatistics at WashU Medicine. With over 300 publications, he leads a dynamic research group that addresses areas such as AI-driven methods for discovering and analyzing biomolecular and clinical phenotypes, interventional applications of electronic health records and clinical decision support, human factors and workflow optimization in healthcare IT, and the development and assessment of data sharing and analytics platforms to support high-value, agile healthcare systems and research initiatives. And so today he'll be speaking with us on leveraging AI to build a scalable learning health system. So I will turn it over to you, Dr. Payne.
Great. Thanks, Mackenzie. I think with that thoroughly embarrassing introduction, with everything you said, I think you covered all the content in my talk. So we'll just go to Q&A now. But nonetheless, I appreciate the invitation. So I'm going to pull up my slides here. I'll start by saying I'm always happy to get a chance to talk with my colleagues in the state of Ohio since before I came here to WashU in St. Louis, I spent 10 years just down the road in Columbus. So it's great to connect with some colleagues and friends on this call. As was said just in the introduction, what I want to do is really talk through some both conceptual models and then practical examples of how we can leverage AI in order to build and operationalize learning health systems, which I think is a fair statement to make an aspirational goal for a lot of us, especially in the context of building and operating CTSAs like this one. So I'll just start with probably a painfully obvious statement, which is it is hard to go more than a few hours without seeing or hearing or discussing in some manner how AI is impacting health and healthcare. And depending on your perspective, this is either the next industrial revolution and one that's going to bring great benefit to our patients and populations. Or alternatively, some people might argue that this is a time of great peril where there are some potentially unintended consequences of the use of AI that we need to be very cognizant about. I will admit, as a source of bias, I am an AI optimist. So I definitely err more on the side of the value proposition of AI, but I am going to attempt to take a pretty balanced approach with this presentation. And I do think it's fair to acknowledge at the outset that there is not universal sort of shared consensus around sort of what the impact of AI will be on health and healthcare over the next several years, if not decades. The one thing that is clear, though, and I already said this, is that if we sort of drill down to the space of sort of the use of information technology, and I would argue by extension data and analytics, the use of AI is dominating almost all of the use cases that we commonly conceive of. But one of the things I do want to call out is that while we often focus on what I'm going to describe as sort of the bright, shiny examples of AI, for example, ambient documentation at the point of care or advanced clinical decision support, in equal measure, behind the scenes, there is a lot of use of AI to automate high friction and potentially low value administrative and operational costs. And I think it is important to sort of realize that those activities, while maybe not quite as glamorous as what we do at the point of care, have a profound impact on the quality, accessibility, safety, and value of care delivery, and are therefore equally important. So when we talk about AI, we don't need to only focus on those things that we see in the clinic or hospital, but really we want to take this broader systems view. Now, for those of you that are not AI people, it's often sort of thought of as sort of very challenging technical domain to sort of become familiar with. In reality, AI is not that complicated from a conceptual level. At the end of the day, what we're talking about is how do we get data and importantly label that data so we understand its meaning? How do we train computational models that can replicate in some way expert human decision making or reasoning across those data? Usually, the advantage that we're looking for is more about speed and scale than it is innate intelligence. And then we're going to take those models where we replicate human decision making using the right data, and we're going to deploy them, whether that be in a laboratory or in a real world setting. We're going to evaluate them. And then importantly, we recognize that the technologies impose changes on these dynamic systems, and therefore we need to monitor and optimize, and then usually refine both the data and the models. And really, if you take nothing else from this slide, this is all about an iterative and continuous process, not a sort of unidirectional development to deployment life cycle. And so, in that way, much like we talk about the virtuous cycle of academic medicine, or we talk about how we sort of translate research into practice and then, sort of repeat those processes, AI is not a lot different. And I only share this because I think, sometimes we get sort of bogged down in the highly technical descriptions of these technologies. But at the end of the day, we're talking about taking data and human reasoning and making it faster and able to work at a greater scale than it ever has before. Now, I mentioned that this is dominating the healthcare and life sciences. That is not the only place that AI is dominating. Here you can see sort of the prototypical hype cycle curve that is produced by our friends at Gartner. And the thing I will point out here is that across the board, the increased capability of AI today has finally caught up with sort of the promise or desired outcomes of AI. And we are now starting to see sort of increased benefits at a scale that we have never seen before. So I will not read this slide in excruciating detail, but I do want to point out this reference because it's very important. A lot of people say, well, how do I even get familiar with all the use cases where AI is being used to address needs, especially in the clinical arena? And there's this amazing report, which I think very few people are aware of, from the National Bureau of Economic Research, which talks about the potential impact of AI in healthcare in sort of more of an economic lens. And one of the nice things about this report is it provides a very detailed analysis of all the different domains of use, sort of examples of how AI may enable improvements in those domains. It talks about value, relative sort of maturity of the technologies, and then sort of costs and outcomes. And so I do encourage you, if you're looking for sort of a source to think about, how do I categorize or think about the types of problems, at least in the clinical arena where I'm going to use AI, this is a great resource. This figure is taken from an analysis of the use of AI in the inpatient setting, and in a similar way, the report also covers a variety of use cases in the ambulatory or outpatient setting. I think one of the important takeaways from this, again, is that these are uses of AI to improve care delivery. They also have a profound impact on our ability to conduct research and understand outcomes and improve quality and safety. And so, again, in that virtuous sort of cycle paradigm, I think the same basic concept exists here. Now, one of the most sort of visible types of AI that people are focused on today are large language models. And I'm hopeful everyone in this audience has probably experimented or used a large language model. It would be pretty shocking if you haven't at this point, since they become relatively ubiquitous. You're probably familiar with tools like those from OpenAI, from Google, from Meta, and a variety of other sort of organizations. But the one basic concept here, and I mentioned that AI is about replicating human decision making, is that large language models allow us to look at large corpora of text in particular, although we can apply these same methods to images, video, and audio as well. And they identify patterns within those large corpora that can be used to produce sort of a model of the language of interest. That language could be written words, it could be spoken words, it could be a visual representation. And what it allows us to do is basically predict the ideal outcome given an input parameter set, right? Now, if you're using ChatGPT, that's basically the question that you ask it or the prompt. The reason why I bring this up is that in large language models, what we're really doing is predicting what the model believes, and I use that word somewhat lightly, the desirable outcome is based upon that input sort of set of content. And so that means large language models are just as good as the input content that we use to train and build them. The other thing I would point out is today, with sort of the rapid explosion in large language models, at least in the textual space, that one of the rate limiting steps in improving the performance of these models is the availability of more unlabeled or even better labeled text to be able to train them. A great example is right now at OpenAI, they are literally creating textual transcripts of large amounts of video data that is historically available just to produce more text to train their text models. So they basically run out of freely available text to train on. I also want to point out, though, that it remains to be seen, although there's some early stage research now, it remains to be seen how customized models that specifically target the needs of sort of the health and life sciences will perform as opposed to these general purpose models. If you look at most of the papers that have been written about the use of large language models today, for example, to extract phenotypes from the electronic health record, they are by and large using foundational models trained on the contents of the general internet, right? So this is basically a model that is predicting an outcome based upon things that might be found in Wikipedia or in social media posts. Not to say that those aren't valuable, but I would say there's a tremendous opportunity for improvement of large language model performance over time as a function of building more domain-specific models in the health and life sciences. Imagine, for example, if we built a model trained on the contents of multiple electronic health records. That would be a very interesting experiment and one lots of people are working on today. But I just use this as an example, again, kind of demystifying the construction of large language models as sort of a subset of that broader AI conceptual model I introduced a few slides ago. Now, this is a picture I sort of love because this is a little bit of a sort of parlor trick. But I asked GPT, actually, this is before they renamed the engine, to produce an image, right? Because it's not just text, it can also be images. An image of a doctor diagnosing a patient with the help of AI technology. So like at a surface level, this is pretty cool, right? We have people using holograms and computers and sort of looking at a systems level of all the things that are going on with this patient. However, and if we were in person, I would probably pause here and ask people to comment. Um, if you take like a closer look at this picture, there are some idiosyncrasies in it. I'll draw your attention to one of my favorites. If you look at the physician in the foreground, or at least the person we might assume is a physician based on their white coat, their body is actually bisected by the exam table. Like it would be physically impossible, as best as one can tell from this vantage point, for someone to sit in the manner that they're sitting. So why am I pointing that out? Because I think this is sort of the current state of large language models. Really impressive performance. Clearly, from a face validity standpoint, producing content that should be of value, right? This picture is impressive overall. But where sort of the idiosyncrasies of large language models manifest today are in the details. And I'll talk more about that, like the detail of how a human being would actually sit on a exam table, or some of the other factors. For example, that despite all the computational horsepower in the world, ChatGPT cannot spell the word diagnostic. So I just use that as sort of a starting point for sort of the trust but verify approach that I want to talk about in the context of large language models. At the end of the day, whether it is a predictive model, for example, using machine learning to drive decision support, or whether it's using a large language model to phenotype patients or process images, today, I believe that the appropriate and sort of optimal use of AI is to enhance human decision making and not replace humans. There are a small number of examples that are contrary to that, but overall, the current state is one where it is the human and computer working together that is superior to either working alone. And so I think it is important to conceptualize how we use AI given that sort of realization. One of the reasons for this is that if you sort of dig into the cognitive science of how humans reason on the information world around them, they really do that through pattern recognition. So my favorite example of that is if you walk into a room and there's a table in that room, you don't have an encyclopedic knowledge in your head of what every table in the world looks like. What you actually have is a set of patterns that you've learned over time, that a table may have a top and legs, and if I set something on it, it will likely not fall off onto the floor. And you use those patterns to assign that label to the object that it is a table, right? This is the human sort of cognitive superpower, the ability to apply pattern recognition, often with missing, incomplete, or fuzzy data, to reason on a very complex information world around us. And when we talk about computers replicating expert human decision making, what we're really trying to do, like I said earlier, is get those patterns represented in a way that a computer can reason upon them, perhaps faster or at greater scale. But computers do have limitations, and those limitations don't go away, even with sort of the explosion of AI capabilities. Certainly, the potential for bias. If we use biased data to train an AI algorithm, we will get a biased result. Sometimes, as I said earlier, we simply don't have the data or the labels on that data to be able to train the algorithm. So that is a limiting factor. Sometimes the cost of even building these models is prohibitive. There are estimates that sort of future releases of most of the major large language models may cost on the order of tens, if not hundreds of billions of dollars to train in terms of the computational costs. And by the way, that is a proxy for environmental impact because underpinning that cost is things like heat and energy consumption. And so these are not benign issues to navigate. And I think it's important to recognize that AI is a continuous process. So we have to continually refine and improve those models. And it's because of those limitations that there are still times and places where humans' ability to reason on fuzzy or incomplete data is superior to that of AI. But on the flip side, human beings have fundamental limitations. Like we are on average only able to recall and reason on seven plus or minus 1 to 2 pieces of information at any point in time. There are very few complex clinical decisions that can be made with only 7 pieces of information. So one of the benefits of AI in that context is that it can help us organize and deliver the right information at the right time to employ those human cognitive superpowers. So I just want to point out, with rare exception, this is really the state of the art, humans and computers working together. And that leads us to the second part of the theme for this talk, which is learning health systems. So I'm sure all of you are quite familiar with the sort of voluminous number of publications concerning why we can and should build learning health systems. And the simplest way of thinking about this is these are health systems where every time we interact with the patient, it's an opportunity to learn and improve. And improve in terms of the care that patient receives, their family receives, or the community receives. And ultimately, this is about creating a feedback cycle that enables what actually Peter Emby and I once described as evidence generating medicine. So instead of talking about evidence based medicine as sort of this unidirectional flow where we do research and evidence is produced and then handed off to providers at the point of care, never to see sort of the light of research again. Instead, in an evidence generating medicine paradigm, we are constantly cycling back from what we see at the point of care and improving that evidence base and then delivering it very quickly in the right time, place, and format to inform decision making going forward. But one of the really important things here is that, first, a lot of people will talk about a learning health system. They almost think about a physical environment, like we're going to build a learning health system. A learning health system is not a physical or built space. It is a series of behaviors that we are promoting and enabling such that that research cycle, that evidence generating cycle gets shorter and faster and more agile. And because this is a very complex environment, I believe that AI provides the ideal set of foundational capabilities to collect, organize, and deliver all of that data in a way that makes the learning health system practicable. So I'm a visual learner, so I like to think of the learning health system a little bit more as this slide lays out, in that we have sort of our operations and research activities. They produce data. We may often use data science and biomedical informatics methods in order to gain insights from those data. That set of insights combined with the right context can be delivered as information. Again, this is where decision and implementation science becomes very critical. We may deliver it through a variety of mechanisms, the EHR, other sort of information systems. And then that ultimately becomes, if we deliver it in the right time, place, and format, actionable knowledge. Again, we can study sort of how that transforms clinical care delivery activities. Ideally, we're going to instrument those activities so we can evaluate and optimize them. And that will allow us to assess impact, which in turn creates more data, and we can repeat that process again. And a sort of overlying theme with this is the idea that this is a data, information, and knowledge intensive environment. We want to use humans working with computers to make this, as I said early, practicable. And AI is at the core of being able to do that because of its ability to organize and deliver data at a scale and speed that exceeds human capabilities. So this is in fact sort of the, if you sort of, again, like me, are visual learners, sort of the cheat sheet view of a learning health system in action. However, you might look at that and say, well, Philip, that sounds great. Why aren't we already doing that? Like that seems self-evident that we should learn and improve. Well, I think that there are 4 really critical questions that we have to ask and answer in order to realize that model that I just described. So first and foremost is not all tasks in the health and life sciences are equal in terms of their suitability for this type of automation and data-driven decision making. So we have to start by saying, are the tasks that we're seeking to focus on in this learning health system the right tasks? Even if we find the right tasks, the next question is, do we have the right data? We might identify a task that's highly amenable to the use of AI to enable learning health system-like behaviors. But if we don't have enough data or the data is not in an actionable format, we may not be able to do that. Even then, if we have the right task and the right data, what's the evidence standard? What are we comparing the performance of these sort of AI-driven capabilities to? And I'm going to get into that a little bit, but I will tell you, I think this is an area where we all need to redouble our focus from a research and innovation standpoint, because we are often using comparators around the use of AI that actually, if we sort of think about them critically, are not the right comparators. And then finally, even if we overcome those first three questions, if we can't deliver the output of these processes in the right time, place, and format, as I said earlier, we will still fail. I say this to my students all the time. You could have the most elegant algorithm in the world, but if people can't use it in the real world, it is still a failure. Being computationally effective and impactful is not a synonym for success. Real world use and impact and outcomes is where really all these pieces come together. So let's dig into those questions in a little bit more detail. And let's start with this first question. How do we find the right sort of tasks within the broader health and life sciences continuum that are amenable to the use of these types of technologies to enable learning health system-like behaviors? So here's an example of a recent study, and I'm going to use a few examples from our group here at WashU to illustrate these points. But this is a project where we looked at data from our Alzheimer's disease clinics and research center. And the question was, could we find patterns in a combination of EHR, imaging, and then cognitive behavioral instruments that would allow us to identify the different transitions in sort of symptom severity and manifestation for patients with Alzheimer's disease like dementia? And the takeaway was that our clinicians felt that there was more heterogeneity in terms of these pathways than we had originally imagined there would be. And that if we could model them, they might allow us to tailor decision support around what types of intervention strategies to use. Well, the takeaway from this, and using an unsupervised clustering approach, we were able to find that the progression of these symptoms in large numbers of Alzheimer's disease patients was indeed highly heterogeneous, that it was not linear, but there were clear reproducible patterns or subphenotypes of patients with ADD that could be used to anticipate who was going to progress more rapidly. And in particular, who had sort of a slower, more linear increase in sort of symptom severity versus those individuals that might have a stepwise increase, whereby there were sort of rapid changes in cognitive function and quality of life and clinical outcomes for those individuals. So I share this because this is an example where the data tells us that there's a pattern and that that pattern may be actionable for improving the way in which we diagnose and manage patients, in this case, with dementia. Here's another example. Now we're going to shift focus. We're not going to talk about patients, but now we're actually going to talk about basically how do we manage the combination of patients and providers interacting in the perioperative domain. So in this case, we actually use large language models applied to post-operative notes in order to understand, was there sufficient information in those notes to anticipate in the first 24, 48, 72 hours post-surgically common complications. So these might be things like DVT or other sort of non-desirable outcomes for a post-surgical patient. And the takeaway here was this was a naive approach, basically knowing a set of potential negative outcomes for patients undergoing major surgical procedures. Did the data exist within the notes that were generated during the sort of perioperative course to predict those outcomes? And the takeaway from this study, again, is that in fact that data does exist in that semi or unstructured format in those notes, and that it can be used to produce predictive algorithms with accuracy in excess of 80% to anticipate these sort of deleterious outcomes for patients in the first 24, 48, 72 hours post-surgically. So this is an example, again, where the data tells us that there is a pattern and that that pattern may be useful in improving the quality, safety, and outcomes of care. And again, now I'm going to go up one level. Now I'm not going to focus on patients at all. I'm actually going to talk about providers. So we know that burnout, medical error, and workforce wellness are major factors in the healthcare delivery environment today. And we also know from some prior studies that those individuals that are experiencing burnout have a much higher probability of making errors, especially during order entry in the electronic health record. And this can lead to things like wrong patient medication errors, where we actually order the wrong medication from the wrong patient because of a task mismatch when someone is entering orders into the electronic health record. So one of the things we want to know is what was sort of exacerbating some of these phenomena, and is there a way to intervene? So we had a hypothesis that the use of secure messaging within the EHR, basically secure chat, which is something we promote the use of for patient privacy and continuity of care issues, whether or not secure messaging actually impacted cognitive load and in turn contributed to both burnout and potentially these types of ordering errors. And the takeaway is it absolutely does. So the reality is that the sort of normative behavior of most providers in our integrated delivery system was when they received a secure message, if they were in the middle of writing orders, they would pause what they were doing, answer the secure message, return to order entry, and the more messages and interruptions they had, the higher probability that they would actually make a error in that order entry task, right? Now, this makes sense based on sort of fundamental cognitive science principles, because we know that cognitive load is a function of sort of having multiple input streams of information, reasoning, task, communication pathways, etc. But I think what's important here again is this is something we were able to discover and quantify using the log files from our electronic health record and understand sort of where those risks existed and how they might be detected, and therefore, more importantly, how we might formulate an intervention strategy. One of the intervention strategies might be that we might mute certain secure messages while someone's in the midst of an order entry task so that we avoid that additional cognitive load. So this is an example now at the provider level, especially from a provider wellness, burnout, and sort of safety standpoint, where we can use data to find a task that seems amenable to automation in this sort of learning health system context. So now let's go to that next question. Let's say we found some tasks, they're interesting. We may want to intervene in this learning health system context. Now the question is there enough of that data? Maybe there's enough data to see the signal, but is there enough data to train a AI tool or digital health intervention that would allow us to improve outcomes or some other sort of indicator of interest? So here's an example of a project that focuses now in the developmental disability space in the case of children with autism spectrum burden. And one of the things that we learned is that if you look at sort of the contents of the electronic health record for individuals with autism, it is increasingly the case that there's insufficient information in the health record alone in order to build accurate predictive models for both disease severity as well as sort of intervention effectiveness. So in this case, what we actually did was build a specialized registry that combined genomic testing data, clinical data from the EHR, and then a rapid neurobehavioral phenotyping tool that can be delivered via virtual care modalities to build a registry of high quality, comprehensive neurobehavioral phenotyping data to build these predictive models. And the reason why I bring this up is it is not always the case that the data exists in the EHR. And this is a case where it is necessary to augment and enhance the EHR to have sufficient high quality, complete, and labeled data to build predictive models. Another example, and I'm sure you're all familiar with the various PCORNet clinical data networks, is that sometimes we really need to think across multiple sites, especially when we think about sort of rare outcomes, rare diseases, other sort of complex phenotypes. So here, one of the things we did was look in the sort of PCORI CRN that we are part of, the GPC or Greater Plains Collaborative, to see whether or not we could replicate the data capture that we have in our cancer registries regionally by using EHR-driven phenotyping. So the question was, if you applied a combination of AI and other sort of data mining techniques to the contents of the EHR, could you automate the process of populating what looks and feels like a cancer registry rather than having to wait months or years? Because cancer registries, by and large, are a function of sort of manual curation, and so that data can lag significantly from sort of the current state of clinical care delivery. And the takeaway here is that you need enough data with enough heterogeneity across enough sites in order to prove that this can actually be done. So this is a case where we use a federated data network, in this case, as I said, the GPC, in order to combine data and actually replicate manual chart abstraction for a cancer registry using AI combined with sort of other data science methods in the context of multiple EHRs. And then this is sort of now taking that up to the next level. I think there are a lot of other uses of generative AI, largely large language models, to be able to extract data that previously has not been computable or appropriately labeled in the electronic health record or other clinical systems. And this is an example of a great study that was run working with the CTSA consortium to look at all of the different use cases where large language models could be used for deeper phenotyping of patients and populations, again, using these advanced AI methods. I think this is a great paper if you want sort of a cheat sheet of what your colleagues are looking at. And I think the real takeaway is there is a broad scope of potential use cases for generative AI to produce even more data than we've ever had before that is appropriately labeled and therefore can be used to build these AI interventions. So now, perhaps we found some tasks where there are signals in our data that tell us that they are amenable to the use of AI or digital interventions. And maybe we found the right data set. That could be through federated learning, it could be through registries, it could be through the application of LLMs to the EHR, it could be just using a conventional data warehouse or all of those things. Now, let's imagine we built some sort of digital health intervention and we want to know if it works. And I think this is something I alluded to earlier is a very difficult problem. So this is one of my favorite quotes from my colleague Karandeep Singh at UC San Diego. He's the Chief Health AI Officer there. It's the only slide I'm going to read verbatim, which is research models are rarely implemented and implemented models are rarely researched. So I want you to think about that. The reality is the models that we know the most about in terms of their performance parameters, how to optimize them, how to get the desired results, often languish in a research setting. And in contrast, many of the models, for example, AI interventions that we use at the point of care today, come from our vendor colleagues and are very poorly studied and understood in terms of their performance envelope. This is creating a situation where we are losing the opportunity to intervene using AI, and simultaneously it's creating a trust gap in terms of the performance of AI at the point of care because we're often giving our clinician colleagues AI tools that are suboptimal. So this is, in my opinion, the current state of play in most institutions. Case in point, this is a pretty well-known study from 2021, which looked at a sepsis early warning system provided by our favorite EHR vendor, and basically demonstrated that this system was basically only slightly better than a flip of a coin, just to kind of cut to the chase. And the reason is that AI models are very difficult to translate across multiple settings and populations. And if you optimize for sort of minimal, for example, false positive or false negative rates, depending on how you optimize the algorithm, you can end up with an algorithm that basically does not exceed what we often refer to as physician global assessment. And what's interesting, you can look at patients that are picked up with having sort of a high EPIC sepsis model score in this case, and you'll actually see that, for example, the adult hospitals that are taking care of them are already ordering more labs and doing more diagnostic workups for those patients because they have assessed with their global assessment that the patient appears sick and they're trying to ascertain why. This is an example of why models don't travel well and why instead of modeling to the lowest common denominator results in a sort of outcome that actually diminishes the value, impact, and trust in AI. Now, you could say, well, maybe that's just because it was like a really big study and there's a lot of heterogeneity in all the different EPIC sites, and that's why it didn't work. But we actually asked that question. So we took that same early warning system and we just implemented it in 9 hospitals using a single instance of EPIC staffed by the same medical staff in one health system, in this case, our health system, BJC. And the spoiler alert is we got the exact same results as that large study that I just alluded to. And the reason why, again, is there's heterogeneity in the populations at those individual hospitals, or they're rural, community, or academic. There is differences in practice patterns even within the same health system. And there's differences in the workflow in which people sort of interact with the EHR. Again, all sort of examples of why getting these models to travel from one site to another is very difficult, and why picking the right evidence standards to decide whether or not the models are successful is so absolutely critical. So, if you say for a minute that the problem is that we're not studying these AI models sufficiently and we need to do that better, what does that involve? Well, what it involves is actually a pretty complicated series of tasks. And this sort of infographic is meant to sort of convey that life cycle. For starters, we should not be building models if we don't actually have a demonstrated need for it. I always tell people if we don't have clinical or operational champions, we need to ask, what is the problem we're trying to solve? I don't know about you, but about every day someone comes to me and they're like, I saw this really great AI model. We should use it. And my first question to them is, what problem are you trying to solve? Don't tell me about the technology. Tell me about the problem that you're trying to tackle. So we need that formal needs assessment. Then we need to go through sort of model development, and there's a lot of sort of data science specific metrics that we can produce that help us understand how a model performs, at least in a prototype mode. The next thing we have to do, and this is the trust but verify stage, is validate the model, often with sort of independent local data or external data. Maybe that's national, global, or otherwise. And then, if we get to the point that we are confident in the model performance, not only with our own data, but perhaps with other comparable data, then we need to figure out how to implement it in the EHR. This is a huge challenge today. It can take, in some cases, up to a year or more to get a model that has been developed and demonstrated in the lab to operate inside a major commercial EHR effectively. And then, even if we do that, we still have to figure out what I think is sort of inappropriately described as the last mile problem, which is tackling all of the workflow and socio-technical considerations that surround the use of the model, right? So if it's delivered at the wrong time, in the wrong place in the workflow, or the results are difficult to interpret, or importantly, there's no actionable intervention strategy, and I'm looking at you sepsis risk models, where even when we have a good sepsis risk model, we don't actually have a good intervention strategy to improve outcomes for those patients, you will lose enthusiasm and buy-in from the people who are going to use those models. So across the board, this is a very complex, resource-intensive process to evaluate these models. So I do want to sort of not end on a negative note about that, but point out that if you do go through that process, you can actually have profoundly impactful results. So this is an example of a study. You remember I talked earlier about sort of our cluster analysis around sort of how we could anticipate sort of disease progression for patients with Alzheimer's disease related dementia. Well, here what we actually did was build a scalable version of that early prototype model that can be shared across multiple participants in a large Alzheimer's disease research network and actually show that we could recreate using reinforcement learning across multiple different sites the same performance. But that's because we went from our local model to validating with a local Alzheimer's disease registry, to validating with the registry maintained by this Alzheimer's disease research network, to then implementing it in multiple EHRs, to evaluating it in those sort of real world settings, and then working with our clinicians to understand how this data would be useful. So this is a very costly and time-intensive process, but if you do it, one of the takeaways is we have a tool today that can substantially improve our ability to provide prognostic sort of reasoning support for our clinicians trying to decide how to treat people with Alzheimer's disease. And I do want to point out that, we don't always have curative strategies for these diseases, but it does not mean that we don't have intervention strategies to improve quality of life, safety, et cetera, for individuals who are experiencing those disease states. Similarly, I would point out we've done the same type of work, in this case, in a rare genetic disease that's common in children, neurofibromatosis type 1, where we now have a multi-site consortia that is doing validation of NF1 predictive algorithms to look at deleterious outcomes like ADHD, optic pathway gliomas, nerve sheath tumors or plexiforms, as well as scoliosis, in order to allow us to have better diagnostic reasoning for children that have this disease. And it's sort of an ideal precision medicine testbed because we're very good at diagnosing NF1, but we are not good at anticipating which clinical outcome kids will have. We tend to monitor very aggressively. And this is a case, again, where we've gone through that whole life cycle that I described earlier, and we are now using reinforcement learning across multiple NF1 clinical centers to show that this can be deployed and used in the EHR to improve outcomes for kids with NF1. By the way, in the past, everybody had tried to look for like a silver bullet, one gene, or sort of one lab test that would predict these outcomes. The reality is this is a multi-scale problem. It takes imaging data, genomic data, clinical data, neurobehavioral data, patient-reported outcomes. All of those data types need to be in play in order to predict these types of outcomes. Okay, so right task, right data. We talked about sort of how we get to sort of the model testing process that gives us sort of the right evidence standard for declaring success, but we still got to get it to people in the right time, place, and format. So that requires what I would describe as sort of prototypical informatics research, which is why we get beyond sort of the technology. So this is an example of a study like that. In this case, looking at the use of an early warning system app for clinical deterioration amongst nursing staff. And of course, in the inpatient setting, the bulk of care is actually delivered by our nursing staff. So delivering these sorts of tools to them is absolutely essential. But this is a prototypical qualitative study You got to give the tool to the nurses. You need to do workflow studies, interviews, mixed methods evaluations, and all of these things, when we put them together, give us a systems level view of what are the barriers to adoption. If you don't do this, you will not identify the predisposing or enabling factors in your environment that are going to make or perhaps not make your project successful. And similarly, this is an example, again, using mixed methods approaches, looking at critical care, and in particular, sort of how we use telemedicine as an augmentation for in-person care in order to improve quality and safety, especially for individuals in the ICU in community or rural hospitals. So in our case, we have an eICU platform. This allows our providers at our academic campus to basically join their colleagues in a exam room or in a actually hospital room at one of our community or rural sites and be a second set of eyes and ears and help work with those care providers to take care of that patient. But again, there are cognitive, workflow, and cultural barriers that have to be overcome to get people comfortable with and to leverage this type of tele ICU intervention alongside more traditional in-person care paradigms. And again, I'm going to go back to sort of that idea of also looking at our providers as an area where we need to improve sort of outcomes and sort of a focus of study. This is again on that sort of theme of using log files. In this case, what we've actually shown is that you can basically use transformer-based technologies, just like we do in large language models, in order to produce more detailed understanding of how individuals interact with the EHR and what sources are of potential error or burnout as a function of that user interface experience, right? So this is about higher order interrogation of the log files of the EHR to identify opportunities to improve that experience for our providers and care teams. So let's go back to sort of the first premise of this talk. Um, I'm going to argue, and I hope that I've at least convinced you in part, maybe not in whole, but at least in part, that if we want to build a fair, inclusive, sort of, AI-enabled system that really is sort of a learning health system, then we do have to overcome hype and focus on sort of rigorous inquiry around the use of AI in this space. And we also have to sort of recognize sort of our unique role in academic health centers. And I want to sort of get into that in a little bit more detail. So, first and foremost, I haven't spent a lot of time in this talk addressing some of the ethical, legal, and social implications of AI in the context of learning health system, but they are significant and absolutely essential. I've been very fortunate, along with a group of colleagues, to be part of a multi-year National Academy of Medicine project to actually build a artificial intelligence code of conduct. And I think what's important here is it's about a set of expected behaviors. And the reason for that is that we today don't know all of the unintended or frankly even intended consequences of AI. So building sort of hard and fast rules and guidelines is extremely hard. But if you think about sort of behaviors that we want to promote and incentivize for the people that develop, use, evaluate, and consume AI, that is something that we can anchor on. And you can see here in sort of box 2 that's highlighted a set of absolutely critical learning health system core principles from prior work at the National Academy of Medicine that directly map to the ethical, inclusive, and appropriate use of AI in the health and life sciences. And I will say, if you want to sort of dig into this topic deeper, I really encourage you to take a look. We had a recent commentary that we published in Health Affairs around sort of priorities for research and development around the ethical and inclusive use of AI in the health and life sciences. And then we actually just released the final report from the group, which is available on the NAM website, which provides sort of the full rubric and sort of framework for that code of conduct and set of expected behaviors. I think today, when we try to tackle these ethical and legal and social implications of AI, arriving at a shared set of expectations for behaviors is probably our best approach. I'm not only saying that because I participate in this group, but because I think attempts to regulate so far have largely been unsuccessful because of the complexity of sort of the domain that they are attempting to regulate. One need only look as far as sort of attempts by the FDA to regulate AI-enabled clinical decision support, which tries to treat it as sort of a typical medical device, which is static and fixed in time, which is antithetical to the way that AI works, as an example of why regulating in this domain is so hard. And I'm not saying we won't arrive at critical regulations, but I'm not sure that we are there yet with our sort of understanding of these technologies. The other thing, as I mentioned, other than sort of being fair and inclusive and thinking about the ethical and legal and social implications, is we do have to overcome hype. And I started with that sort of parlor trick where I showed you that GPT generated image where like the person was, being bisected by the table, and there was some other weird features. But let me give you another example of why we need to be careful and not sort of fall into that hype cycle. So here's a prompt that I entered into GPT-4o, which was list the most important academic papers that I, Philip Payne at Washington University, has written. And here's the result that came out. Again, if I was in the room, I would poll you all and say, how many of these papers do you think are real? And usually when I ask that question, people say, oh, maybe 3 or 4 of these papers. None of these papers are real. So the reality is back to the idea that it's predicting sort of the outcome of interest. Here, what it's done is predict a set of titles that if you read them, my first reaction is I probably should have written these papers. They don't sound like bad papers. Like they're pretty much on target for the type of research that I'm involved in and the areas that I'm focused upon. But they are not papers that I've written. And so my point is, it's like this is almost sort of an illustration of why these sorts of technologies are really good as a hypothesis generating tool, but maybe not one for answering concrete questions that require factual answers. So I bring this up like we need to understand where these tools excel and where they don't. I will tell you in the research domain, I am not as bothered by, for example, issues such as hallucinations, because hallucinations might be another term for hypothesis generation in that context. And that would be okay given the use case. In contrast, if I was at the point of care and I said, give me a paper that I can read to help me understand this rare disease that I'm trying to diagnose and treat, this would be bad. So it's all about context. But this is why falling into the hype cycle is something that we need to avoid. I'll also just say that sort of looking forward, some of the work in front of us is not just about sort of building better models or addressing those evidence standards or sort of enabling the learning health system. We also need to tackle some of the fundamental implementation science that underpin bringing these types of complex dynamic technologies into the clinical environment or into the research environment or into the teaching environment. And one thing I do want to call out is this great paper by Chris Longhurst and colleagues that really is a call to action to our broad community, not just informatics, but the entire health and life sciences community about why we need to build centers of excellence to be able to look at clinical effectiveness. And if I was giving you a different talk, I would spend a lot of time talking about what are the right outcomes measures for AI? Because I will tell you, when we do things like say, how does AI compare to a human gold standard today, where that human gold standard is intrinsically flawed, right? Because humans are not perfect. They don't make accurate decisions every single time. They omit information. They have biases. I could keep on going down the list. We're probably asking the wrong question. We should be asking questions like, what is the impact on quality, safety, outcomes, value of care, and how do we quantify that? And that requires, again, rigorous inquiry. And then I'll just lastly say there are all sorts of sort of organizational, political, and leadership issues that underpin our ability to build these types of learning health systems. This is a merciless self-reference to a paper that I wrote with a group of colleagues across a number of different academic health centers, trying to illuminate sort of critical needs in terms of leadership structure and operating in order to be able to effectively implement and evaluate AI at scale. And this is an unsolved problem. Very few organizations, my own included, have fully sort of conceptualized how to do this work in an effective, agile, and resource efficient way. So I'll just sort of wrap up by saying, first and foremost, I presented a lot of work here from a group of fantastic colleagues and collaborators at WashU that I work with, including the people in my own laboratory. You see a few pictures of them here, a number of really critical collaborators, as well as sort of our other sort of partners and funders across the university and the NIH. And with that, I'm going to sort of hop out of the presentation view so I can actually see you all. And I am happy to answer any questions that you might have. While you're thinking, I'm sorry, Alex, do you want to say your question that you wrote in the chat thread?
Sure. You covered this a little bit in the last part of the presentation, but the question was, are there any recommendations you make on the way to combat the increasing rates of the hallucinations, the false data among each new iteration of reasoning models? And I linked a paper that talked about the differences between OpenAI models 3 and 4, which increased hallucination from 33% of the time of use to 48% of the time of use.
Yeah,
And
great question. I would say there's a couple things at play there, right? So I'm going to first start to talk about how the foundational models are being built. So we are starting to enter into an era where we have a lot, and I just recently heard this term, which I love, that we're experiencing a lot of what is referred to as AI slop, right? So this is where it's such a great term. This is where we're basically getting sort of content that's AI generated proliferating in sort of the public internet, such that these foundational models are being trained on AI generated content. Not surprisingly, that will substantially magnify sort of the existence of hallucinations. It's the same thing I mentioned earlier, where companies like OpenAI, because they're running out of sort of available text to train their models, are now doing things like using AI to extract text from video and audio. So they're introducing hallucinations into sort of that training data set. I think in the health and life sciences, the real question is, do we need to start building smaller, more domain specific and curated models where we understand the training data rather than using those foundational models? And I think it depends on the use case. Like I said earlier, like if it was hypothesis generating, maybe I'm a little bit more tolerant of sort of the impact of sort of hallucinations. Whereas perhaps if it's clinical decision making, it's different. And I know in our own group, we are deeply invested in sort of the use of, retrieval augmented generation methods that overlay sort of highly curated knowledge networks on top of the large language models to help combat some of this problem as well. That is a very costly way to build and reason, but I think it's sort of our best bet today. The second thing I already alluded to is like understanding the use case, right? So like, what is your risk tolerance for, sort of hallucinations, depending on the way in which you're going to use it. And then I think the last part of it is, this sounds like such a flippant answer, but like prompt engineering matters, right? Now, I'm not one of those people that thinks we should be creating like degree programs in prompt engineering, even though some universities have tried to do that. But what I do think is we need to be very smart about that, right? So there are ways to tailor our prompts to do things like anchor the results that are generated on real world references and provide me the URLs from those references, right? So I can basically use sort of a reasoning sort of or decision analysis method to look at sort of the sourcing of that content and basically validate. So that's a place, and actually goes to my like, humans and computers working together where, that's not a 100% automatable process. So again, I'll reiterate, I think it's thinking about the use case. I think it's like dealing with AI slop and how do we overcome that in terms of the training of foundational models and maybe look at more tailored models. And then how do we get smarter about prompt engineering? That's like the three best answers right now. They're not great answers, right? I wish there were better answers. But I think there's a tremendous amount of great research going on right now about how to sort of detect and understand these problems. So hopefully that answers in part the question. I'm looking at, so Samuel put in with more EHRs now collecting symptom data and patient-reported outcomes, especially in cancer care. Have there been AI applications to identify and recommend treatments to patients with high symptom burden? So yes, I think it's actually a very interesting space, especially when we bring together sort of patient-reported outcomes data alongside sort of symptomology from the EHR. Cancer is one of those spaces where, in particular, patient preference is a sort of co-equal part of the decision-making process alongside sort of evidence-based sort of practice guidelines and then sort of clinical acumen and judgment. And, one of the things that AI can do is help us to bring together sort of those component pieces and present them in a way that helps guide that decision making. In our own institution, we have a prototype. It's not directly applicable to, this example, but I think it's in the neighborhood, which is that we've actually built a predictive model that looks at patients with high chronic or acute disease burden. It includes a lot of patients with cancer that present in the emergency department and appear to be on a trajectory for direct admission to the ICU. And we know that the mortality rate is extremely high for those patients. This could be an advanced cancer patient, shows up in the ED, and the pathway is put them in, an oncology ICU. What we're actually doing there, which is not about cancer treatment, this is where we kind of diverge from the question, is we're actually triggering a order set to have a palliative care consult in the emergency department and talk about goals of care before the direct admission to the ICU. We've actually diverted probably close to 100 patients in the last 12 months in one of our community hospitals in order to sort of move them into palliative or hospice care. And those patients and their families actually report improved end of life experience as opposed to sort of going to the ICU. So that's an example of sort of using our understanding of patient-reported outcomes, preference, symptomology, and triggering sort of a targeted intervention to improve outcomes for those patients. All right, Satya, do you want to ask your question?
Yeah, so a great talk as always, Philip. So I had a broad philosophical question. One of the challenges we are facing, of course, is separating out the AI slop from the reality. Given the fast-moving changes that are happening, how do you make sure that clinicians and our collaborators are aware that many of the what's in the popular media may or may not be true? That's the positive as well as the negative. For example, there was this lot of talk in terms of it's a black box, but now you have these reasoning models. We're moving into in that context. What are broadly at a system level, at an institution level, we can do to encourage more interaction so the positive and the negative is more balanced? And
Yeah.
again, given your experience with the EHR systems, there's a parallel sort of discussion along those lines.
Yeah, so I think for starters, I would say like we should not recreate the process that we use to give EHRs to clinicians, right? I always tell people we gave EHRs to clinicians like we took a human who had never seen a car on the road, they wanted to drive, and we're like, here's a car and here's the keys and there's the pedals, good luck, right? We never actually taught anyone how to drive. We just gave them the constituent pieces. And I think we need to not do that with AI, right? We can't deploy it like it's just another technology. I wish I had like a magic answer to what you're saying. I will tell you some of the things that we're doing. We have started embedding sort of training on AI sort of competencies and how to critically interpret AI generated content into our new medical school curriculum. So we're training our newest physicians how to be critical consumers, no different than how we train them to be critical consumers of scientific literature. We are providing sort of basically what I describe as like almost like an AI mini grand rounds where we use sort of clinical correlates where we say, here's a clinical problem that a clinician was trying to solve, right? And here's how they used AI. And we have the clinician tell the story, not the technologist, not the data people, right? Sometimes we even get the patients involved if they're willing to do so. And then I think the third thing is like we are really working hard. Like this is like the shoe leather politics. We're just really working hard on our communication strategy. Like we are just communicating every vehicle we can about what we're doing in the center, how to ask questions. Here's the projects we're working on. We will do whatever we can in order to communicate. And I think that is the biggest thing, not to repeat the errors of EHR deployment and to just find ways to reach people. And people are busy. Right. So like you have to use like multi-channel communications. Like it's not just social, it's not just seminars, it's not just web, it's all of that and more. And so I actually have hired a number of communication strategists as part of our Center for Health AI. That's all they do is focus on how do we reach those targeted communities. And I don't want to leave out, before I know we're out of time, also our community. Right. So we are very focused on working with our community advisory boards, our patient advocacy groups, et cetera, to also talk to them, right? Because there's a very real and meaningful concern about how we're using AI in the clinical environment and what that means. And I don't think anybody should take it for granted that, it is our decision alone to bring these tools into the clinical environment.
Great. Thank you.
Well, thank you so much, Dr. Payne. That was a great presentation. For the sake of time, we will close out the seminar. And I hope everyone has a great day.